NENOMATICA, where mathematics meets YouTube excellence. In this video, we will follow method 2 for rationalizing a denominator that contains square roots. We'll reproduce the exact algorithm, show the target denominator, multiply by its conjugate, and recall common conjugate pairs. Then we will write the headline in orange. Step 1. Express the denominator explicitly in the form square root of a plus or minus square root of b. This clarifies the exact conjugate we need in the next step. Step 2. Multiply numerator and denominator by the conjugate of the denominator. For a denominator of square root of a plus square root of b, the conjugate is square root of a minus square root of b. The product simplifies by the difference of squares. Parentheses square root of a plus square root of b parentheses times parentheses square root of a minus square root of b parentheses equals a minus b. Now the second case. If the denominator is square root of a minus square root of b, multiply by square root of a plus square root of b, the matching conjugate. Again, the denominator becomes a minus b. Step 3. Recall common conjugate pairs. You can use beyond square roots. We often see a minus square root of b and a plus square root of b, square root of a minus square root of b, and square root of a plus square root of b, and even fourth roots paired in the same way. Summary. For denominators of the form square root of a plus or minus square root of b, multiply by the conjugate to convert the denominator to a simple a minus b. In this lesson, we will rationalize denominators step by step, exactly following the standard algorithm using conjugates. Example 1. We start with the fraction open parenthesis square root of a minus 1 close parenthesis over open parenthesis square root of a plus 1 close parenthesis. Step 1. Multiply by the conjugate of the denominator, which is square root of a minus 1, over square root of a minus 1. Step 2. Write the product forms in numerator and denominator. Step 3. Apply the difference of squares in the denominator. Step 4. Simplify the squares to finish. Example 2. Start with a minus b over square root a minus square root b. Step 1. Multiply by the conjugate of the denominator, square root a plus square root b, over itself. Step 2. Write the products in numerator and denominator. Step 3. Again, use the difference of squares in the denominator. Step 4. Simplify, cancel a minus b, and conclude the result. In this lesson, we will rationalize denominators using conjugates. We will follow a clear step-by-step algorithm on 2 examples. The key idea is the difference of squares. When you multiply a plus b by a minus b, the cross terms cancel, and you get a squared minus b squared. This is why multiplying by the conjugate removes square roots from the denominator. Example 1. Rationalize the denominator of 5 over 4 times the square root of x plus the square root of 3. We will multiply top and bottom by the conjugate, 4 times the square root of x minus the square root of 3. Then we will combine, and finally simplify the denominator using the difference of squares. Notice here that it equals 4 times the square root of x, and b equals the square root of 3. Then a squared is 16x, and b squared is 3, so the denominator becomes 16x minus 3. Example 2. Rationalize the denominator of 10 over 3 minus 5 times the square root of x. Multiply by the conjugate 3 plus 5 times the square root of x over itself. Then simplify using the difference of squares. In this lesson, we will simplify and rationalize a sum of 2 fractions that contain square roots in the denominators. Our task is to follow each algebraic step carefully, exactly in the order shown, to reach the final simplified form. Step 1. Combine the 2 fractions over a common denominator. Multiply the first numerator by square root of x, and expand the second numerator by 1 plus square root of x. Step 2. Apply the difference of squares identity. Left parenthesis 1 plus square root of x right parenthesis times left parenthesis 1 minus square root of x right parenthesis equals 1 squared minus the square of square root of x. Then write that inside the numerator exactly. Step 3. Simplify the numerator x plus 1 minus x equals 1. Step 4. Notice the denominator is the product of 1 plus square root of x with square root of x, which equals square root of x plus x. Step 5. Rationalize the denominator by multiplying by the conjugate square root of x minus x divided by square root of x minus x. Step 6. Multiply across. The denominator becomes a difference of squares. Left parenthesis square root of x plus x right parenthesis times left parenthesis square root of x minus x right parenthesis equals the square root of x minus the square of x. Then simplify the powers. In this lesson, we will rationalize denominators using conjugates. We will do 2 fully worked examples, step by step. The key idea is simple. The conjugate of a plus b is a minus b. Multiplying a binomial by its conjugate produces a difference of squares, a squared minus b squared. Example 1. Rationalize the denominator of 2 divided by the square root of 5 plus the square root of 3. Multiply the top and bottom by the conjugate, which is square root of 5 minus square root of 3. The denominator becomes 5 minus 3 by the difference of squares rule. Now simplify and cancel the common factor of 2 to get the final result. Notice how the denominator became 2 and cancels with the numerators 2. That cancellation is what cleans the denominator. Example 2. Rationalize the denominator of 8 over the square root of 3 minus the square root of 7. Multiply by the conjugate, square root of 3 plus square root of 7, over itself. The denominator becomes 3 minus 7, which is negative 4. Simplify the fraction to get negative 2 times the quantity, square root of 3 plus square root of 7. Here are both final answers side by side. Example. We will follow the exact step-by-step algorithm. Multiply by the conjugate, apply the difference of squares to the denominator, and then simplify. Our tasks are rationalize 5 divided by 2 minus the square root of 3, and rationalize 7 divided by 3 plus the square root of 5. The key rule is the conjugate trick. For any a and positive c, a minus root, c times a plus root, c equals a squared minus c. So to remove a radical from a denominator, multiply numerator and denominator by the conjugate. Now, follow the algorithm for the first fraction. Start with 5 over 2 minus root 3. Multiply by the conjugate 2 plus root 3 over itself. Keep the numerator grouped as 5 times parenthesis 2 plus root 3. The denominator becomes 2 squared minus 3. That is 4 minus 3, which equals 1. So the result is 5 times 2 plus root 3. Second fraction. Start with 7 over 3 plus root 5. Multiply top and bottom by the conjugate 3 minus root 5. Group the numerator as 7 times parenthesis 3 minus root 5. The denominator is 3 squared minus 5. That equals 4. So the simplified result is 7/4 times 3 minus root 5. Here is the expression. The first factor is open parenthesis square root 3 minus square root 2 close parenthesis raised to the power square root 2 plus 1. The second factor is open parenthesis square root 3 plus square root 2 close parenthesis raised to the power 1 over square root 2 minus 1. Step 1. Rationalize the exponent 1 over square root 2 minus 1 by multiplying numerator and denominator by the conjugate, square root 2 plus 1. This gives square root 2 plus 1 over 2 minus 1, which equals square root 2 plus 1. Therefore, the exponent on the second base equals square root 2 plus 1. So the entire expression becomes open parenthesis square root 3 minus square root 2 close parenthesis to the power square root 2 plus 1 times open parenthesis square root 3 plus square root 2 close parenthesis to the same power. Step 2. When 2 factors share the same exponent, we can multiply the bases and keep the common exponent. So a to the m times b to the m equals ab to the m. Applying this here gives the product of the conjugates all raised to the power square root 2 plus 1. Step 3. Conjugates multiply to a difference of squares. Here alpha equals square root 3 and beta equals square root 2. So the inside becomes open parenthesis square root 3 squared minus square root 2 squared close parenthesis to the power square root 2 plus 1. Now square root 3 squared is 3 and square root 2 squared is 2. So we get 3 minus 2 raised to the power square root 2 plus 1, which is 1 to that power. Any positive real number 1 raised to any real power remains 1. Therefore, the value of the original expression is exactly 1. In this example, we will prove a neat algebraic identity that looks a bit mysterious at first. We are given the product of two expressions equals 1, and we will show that x plus y must equal 0. Let's write the problem, and then build intuition step by step. The heart of this problem is a simple but powerful identity. Define f of t as t plus the square root of t squared plus 1. Then f of t times f of negative t equals 1. Let's expand to see why this is true. Now apply the identity with t equals x. We get x plus square root of x squared plus 1 times negative x plus square root of x squared plus 1 equals 1. Since the given product also equals 1, we can set the two products equal to each other. Notice that x plus square root of x squared plus 1 is strictly positive, so we can cancel it from both sides. That gives us y plus square root of y squared plus 1 equals negative x plus square root of x squared plus 1. By symmetry, repeat the same argument with t equals y. Then y plus square root of y squared plus 1 times negative y plus square root of y squared plus 1 equals 1. Matching the given product again and canceling the positive factor, we obtain x plus square root of x squared plus 1 equals negative y plus square root of y squared plus 1. Great! We now have two linear-looking equations in disguise. Place them side by side and add them term by term. On the left, the square root terms appear once each. On the right, they also appear once each, but with the opposite variables. The square root terms cancel perfectly, leaving 2x plus 2y equals 0. Finally, divide both sides by 2 to get the clean result. In this video, we will prove a beautiful telescoping identity with square roots. For any natural number n, the sum from k equals 1 to n of 1 over the quantity square root of k plus square root of k plus 1 equals square root of n plus 1 minus 1. Let's expand the first few terms to see the structure. We have 1 over 1 plus square root 2, plus 1 over square root 2 plus square root 3, plus 1 over square root 3 plus square root 4, and so on, until 1 over square root north plus square root of n plus 1. Our strategy is to rationalize each denominator using its conjugate. For a plus b, multiply by a minus b over a minus b. Watch it on a typical term. Now simplify. The denominator becomes k plus 1 minus k, which is 1. So the term equals square root of k plus 1 minus square root of k. Applying this to every fraction in our sum gives a string of simple differences. Notice the pattern. This is a classic telescoping series. Each positive square root cancels with the next negative square root. Everything in the middle disappears, leaving only the very first negative one and the very last positive square root of n plus 1. Therefore, the sum from k equals 1 to north of 1 over square root k plus square root k plus 1 equals square root of n plus 1 minus 1. Proven. As a quick check for intuition, take n equals 5. The left-hand side is the sum of 5 fractions, and the right-hand side is square root of 6 minus 1. Both sides are approximately 1.45, and that is the telescoping radicals proof. The conjugate trick turns a difficult-looking sum into a simple difference that collapses beautifully. In this video, we will solve a beautiful telescoping series using rationalization. The final answer will turn out to be the square root of n. Here is the sum s. Read it as 1 plus square root of 2 over 2 plus square root of 2 plus square root of 3 over 3 plus square root of 6, and so on up to the nth term. Step 1. Rationalize a typical term. Start with the second term. Multiply by the conjugate 2 minus square root of 2 over itself. Then simplify. The denominator becomes 4 minus 2, and the numerator simplifies to 2 square root of 2 minus 2, which over 2 is square root of 2 minus 1. Do the same for the third term. Multiply by 3 minus square root of 6 and simplify. The result is square root of 3 minus square root of 2. Notice the pattern. Each term becomes a difference of consecutive roots. Now write the general k, th term. We have square root of k divided by k plus the square root of k times k minus 1, multiplied by the conjugate k minus the square root of k times k minus 1. The denominator becomes k squared minus k times k minus 1, which is k. The numerator simplifies to k times square root of k minus k times square root of k minus 1. After dividing by k, every term reduces to square root of k minus square root of k minus 1. Therefore, the entire sum becomes 1 plus the quantity square root of 2 minus 1, plus square root of 3 minus square root of 2, plus square root of 4 minus square root of 3, and so on up to square root of north minus square root of n minus 1. Watch the telescoping. The minus 1 cancels the initial 1. The minus square root of 2 cancels the plus square root of 2. The minus square root of 3 cancels the plus square root of 3, and so on, leaving only the very last term, square root of n. Therefore, the entire series collapses to the single surviving term. The sum south equals square root of n. Recap. Each fraction simplifies to square root of k minus square root of k minus 1 by multiplying with the conjugate. Those differences cancel in a chain, a classic telescoping pattern, leaving only square root of n. Try this technique on similar sums with nested radicals. In this lesson, we will compute for a symbolic expression by following a clean, step-by-step algebraic algorithm. We will rationalize a denominator, substitute, and finish with a simple piecewise answer in terms of b. Here is the problem. We have a equals the square root of a plus x plus the square root of a minus x, divided by the square root of a plus x minus the square root of a minus x. Also, x equals 2ab over 1 plus b squared. We assume a is greater than 0, and b is not 0. Our goal is to simplify completely. Step 1. Rationalize the denominator by multiplying top and bottom by the conjugate. This turns a difference of square roots into a difference of the arguments. Now expand the square in the numerator and simplify the denominator. The numerator becomes a plus x plus a minus x plus 2 times the square root of the product. The denominator becomes 2x. So a equals a plus the square root of a squared minus x squared, all over x. Next, substitute x equals 2ab over 1 plus b squared. We place it into a equals a plus the square root of a squared minus x squared, all over x. Simplify the radical. Inside the root, we have a squared times 1 minus 4b squared over the square of 1 plus b squared. Because it is strictly positive, the square root of a squared equals, allowing us to remove the absolute value. Notice the identity. 1 plus b squared quantity squared minus 4b squared equals 1 minus b squared quantity squared. Therefore, the numerator becomes a times 1 plus the absolute value of 1 minus b squared over 1 plus b squared. Multiply numerator and denominator by 1 plus b squared to clear the small denominator. We get a equals 1 plus b squared plus the absolute value of 1 minus b squared all over 2b. Now, we split into two simple cases. Case 1, the absolute value opens positive if the magnitude of b is at most 1. Then the absolute value equals 1 minus b squared, and a simplifies to 1 over b, with b not equal to 0. Case 2, if the magnitude of b is greater than 1, the absolute value equals b squared minus 1, and a simplifies to b. Therefore, the final answer is piecewise. A equals 1 over b for negative 1 less than or equal to b less than or equal to 1, with b not 0, and a equals b for b greater than 1 or b less than negative 1. Quick check for intuition. If b equals 1/2, the rule gives a equals 1 over b, which is 2. If b equals 2, the rule gives a equals b, which is 2. Both values are simple and consistent with our formula. Example. In this problem, we will follow the exact algebraic steps shown in the prompt to prove a target identity. The target is what we want to end with. Then we state the given x, 3 minus square root of 2. Now, multiply by the conjugate. We write x equals open parenthesis 3 minus square root 2 close parenthesis times the fraction with 3 plus square root 2 over 3 plus square root 2. Apply the difference of squares. The numerator becomes 9 minus 2. That simplifies to 7. So x equals 7 over 3 plus square root 2. Next, square both sides exactly as shown. we get x squared equals 49 divided by open parenthesis 3 plus square root 2 close parenthesis squared. Now expand the denominator. The square of 3 plus square root 2 is 9 plus 2 plus 6 square root 2. Combine like terms. 9 plus 2 is 11, so the denominator becomes 11 plus 6 square root 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.